Hello, this is Dr. G, and I'm coming at you with another video. If you are a new subscriber or you haven't watched all of the videos, you may not know that I actually live in Florida, and occasionally we get these things called hurricanes. And so you might be wondering, what are the odds of a hurricane hitting Florida? At the time of this recording, we just had a fairly active hurricane season this past year where we had a few hurricanes and we actually lost power at our house briefly. But what I did was I went to the NOAA website, so the National Oceanographic and Atmospheric Association.gov, and I looked up what are chances of a hurricane will hit my home. So this is the photo. And so if you look at the return period for a hurricane, this is the frequency in number of years a location will likely be affected by a hurricane. So if I look here, every 13 years, this area over here, which is kind of the Space Coast, will be hit by a hurricane. Down here over in Miami-Dade, every 6 to 7 years. Over in the Tampa area, you have 10. And then up in the Panhandle, it's every 9 to 11, right? So obviously up near Jacksonville, it's a little less frequent, more frequent down near Miami-Dade, and then up the East Coast, okay? So this is Florida. So our problem is, right, this is our intro to the problem. From the NOAA website, the highest probability in Florida is between 6 and 13, once every 6 years, once every 13 years. So I'm kind of changing that to a probability. So what we're going to do for this problem is use 1/10 as an average for the state, right? Several locations are actually that value, and it's pretty easy to work with, right? So we're going to say the probability of a hurricane hitting us in any given year is 1 in 10. Or the probability of H, a hurricane, in a year is going to be 0.1. So what are the chances a hurricane will hit in the next 10 years? Like I said, this past year, we had a couple of hurricanes. I lost power briefly. And so you might be thinking, do I need to buy a generator? Is it worth the investment to have it in my garage, in my shed, because I'm likely to lose power in the next 10 years? During Hurricane Charlie, we lost power for long enough that we lost all of our food. The amount of food that we lost would have been equal to one generator. So it would have been worth it to have it. Okay? So, but I don't want to just store it forever, right? So the question then becomes, what's the probability of at least one hurricane in 10 years? So do we just add the probability of a hurricane 10 times? Well, if I do that, 0.1 plus 0.1 plus 0.1 plus 0.1, that would be that would be 1. The probability would be 1. The probability of that calculation would be 1. In other words, it would happen. That's not really true, right? Some places go 11, 12, 13 years in between hurricanes, okay? So that's not right, okay? And then what if we get 2 hurricanes or 3 in that 10-year period? It's possible to get 2 or 3 hurricanes in a 10-year period. Look, over here, it's every 6 or 7 years, right? So you could definitely see, and this is the historical average likely to be affected. So maybe more often, like the year that we got Charlie, Jean, Francis, and Ivan that all hit Florida. So 3, right? So the probability of one hurricane is it is not quite this, right? The probability of hurricane isn't just add up the 10 hurricanes, right? The probability of the 2 hurricanes requires actually a combination of the 10 years, and I get to pick 2 of those years to have a hurricane. So it could be the first year and the second year. It could be the first year and the third year, first year and the fourth year. Could be the second year and the third year. How many combinations are those? Well, it turns out that that combination is 45. Well, what about 3, 4, 5, and so on? what would you do? Well, it turns out that the binomial distribution formula comes in really helpful here. Since we only have two outcomes, the hurricane hits you or it doesn't, and because the probability is the same from year to year, we meet the conditions for this binomial distribution. And the distribution gives us the following formula. The probability of X happening is equal to the number of trials that we're looking at times the number of times we're counting that trial. For the probability of success is P, the probability of failure is Q. Now if you look, these exponents here, K is the number of times I'm counting success, N minus K, right, plus K, that if you add these exponents here, that would give you N. So this is the count of the number of failures. So K is the count of the number of successes, N minus K is the count of the number of failures, P is my probability of success, Q is my probability of failure, and this is the way that we would calculate the combinatoric, the number of combinations that I can make, that I can count these number of successes. Okay, so the derivation and an explanation beyond that is really beyond the scope of most courses, unless you're in a theory course or a graduate course. So we're just going to present it here and use it below. Okay, so it turns out that for all combinations possible of 1 hurricane to 10 hurricanes in a 10-year period, right, would be to go, hey, here's my number of hurricanes, the number of hurricanes, at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the 10 years. There's 10 ways of doing 1. There's 45 ways of doing 2. I'm getting that by plugging N is going to be 10. And then for 1 hurricane, K is going to be 1. For 2 hurricanes, K is going to be 2. For 3 hurricanes, K is going to be 3, right? So I have this number of possible combinations. My successes, right, are going to be the probability of success raised to the first power, my probability of success raised to the second power, my probability of success raised to the third power. But the binomial theorem tells us we can't just add these together. We're actually going to multiply it by the failure condition. So that would be 0.9 raised to the 9th power, 10 minus 1, right? This failure is going to be 0.9 raised to the 10 minus 2, or 8, and we go all the way down here. And then what we have to do is we have to multiply our combinations times our probability of success times our probability of failure. So multiplying all those together gives us this partial expected value. And when you add up all of these partial expected values, you get 0.651 blah, blah, blah. And hopefully you looked at this formula and you looked at this table and you're asking yourself, please, there has to be a better way of doing this. And there is an easier way of doing this. And basically it requires you to use the complement rule, and then you can do some basic calculation. So how would I do this using the complement rule, right? Here's what I'm going to do. The probability of a hurricane in a year is still 1/10 or 0.1. This is a very important result from set theory. This is how we derive the complement rule. So this is the complement rule. The probability of at least 1 plus the probability of none, total failure, all 10 years, no hurricane, has to be equal to 1. Because you're either going to get at least 1 hurricane or you got no hurricanes. Those are the only 2 possibilities. By subtracting the probability of none from both sides, I get the probability of at least 1 is equal to 1 minus the probability of none. This is the secret sauce right here. This is the formula that allows us to do some really easy calculations. What is that easy calculation? Well, the probability of none is 0.9, right? So you take 1 minus 0.10 and you get 0.9. So that's the probability of none. Okay? And so the probability of none in 10 years would be none times, right? And, which would mean multiply, none and none and none and none. And so 0.9 raised to the 10th power. And 0.9 raised to the 10th power is 3.349. It's 0.349. So that's the probability of none. So what's the probability of at least one? 1 minus the 0.349, which is 0.651. Wait a minute. That's exactly what we got up here, 3 decimal places. So we get the exact same result, thus providing us with that, the thing that we got in the binomial. Now, we can generalize this. If P is the probability of success, right, and Q is 1 minus P, the probability of failure, then the probability of at least one plus the probability of all failure has to be equal to 1. So this is the probability of none. So for one trial, the probability of at least one is going to be 1 minus the probability of failure. That's literally the complement rule. So what do we do for the probability of at least one when we have more than one trial? It's the probability of 1 minus the probability of failure raised to the k power, where k is the number of trials. And that is what we did here, right? 0.9 is the probability of failure. 10 was the number of trials. This is my probability of none. 1 minus my probability of none gave me my at least one. So this is the generalized way of doing these at least one problems. And now you don't have to derive it each time for each formula. And that makes us happy. If you found this video helpful, if you like this kind of content, please give this video a like. It really helps the channel. And if you have questions or ideas for another video, comment below. I'm always finding an hour or two to put a video together, and I would love to hear all of your thoughts.